So we will now continue our study of vector valued functions by looking at arc length and curvature. So recall that in Calc 2, we studied that the arc length of a curve that was defined by the parametric equations x equals x of t and y equals y of t over the interval t1 to t2 was given as the integral from t1 to t2 square root of x prime squared plus y prime squared. So in a similar fashion, if we define a smooth curve by the vector arc t equals x of t, y t, where a is less than or equal to t, less than or equal to b, the arc length is given as the integral from a to b of the square root of x prime squared plus y prime squared. However, this is just the magnitude of r prime. So the arc length is just the integral from a to b of the magnitude of r prime dt. Now, a smooth curve is a curve in which r prime of t is not equal to 0. Now, this will still hold even if it is a space curve. And so this is our arc length formula. S is equal to the integral from a to b of the magnitude of r prime of t dt. So what we're going to do now is we're going to calculate the arc length of a few curves. So the first curve will be defined by the vector 3t minus 2, 4 plus 5 over the interval 1 to 5. Okay. So first thing we need to do is we need to find r prime of t. Right, so this is just simply the vector 3 comma 4. So the magnitude of r prime would be the square root of 3 squared plus 4 squared. So this is the square root of 25, which is just 5. So the arc length is the integral from 1 to 5 of 5 dt. So this is just 5t evaluated from t equals 1 to 5. So we get 25 minus 5, and the arc length is 20. Next is a space curve defined by t cosine of t, t sine of t, 2t over the interval 0 to 2 pi. And so again, the first thing we need is r prime. Now each of these first two components is a product rule. So it would be cosine of t minus t sine of t. Then it'll be sine of t plus, I don't know what happened there, plus t cosine of t, and then just 2. So the magnitude of r will be the square root of this first component squared. So cosine squared minus 2t cosine sine, then plus t squared sine squared. Plus now the second component squared, so we get sine squared plus 2t sine cosine plus t squared cosine squared, and then finally plus 4. Now this term looks like a bloody nightmare. However, let's just look at a few terms. So here we have a cosine squared, and here we have a plus sine squared, so we can look at those two terms together. Next, let's look at, we have this negative 2t cosine, and we have this positive 2t sine cosine. So we can look at those two terms together. And then we also have this t squared sine squared and this plus t squared cosine squared. So we can look at those two terms. So if we relook at this, we're going to have the square root. Now the yellow terms, cosine squared plus sine squared is just 1. These blue terms, the minus 2t cosine t sine t and this plus 2t sine t cosine t is just 0. Then if we look at these green terms, this t squared sine squared plus t squared cosine squared is just plus t squared. And then of course we still have that plus 4 floating around. So this is now the square root of t squared plus 5. So the arc length will be defined as the integral from 0 to 2 pi of the square root of t squared plus 5 dt. Now, there are a couple ways we can go about tackling this integral. We could use the techniques of Calculus 2, specifically trigonometric substitution. However, there was also a technique that was just reading an integral table, and that's actually the technique I'm going to use. So, the integral table gives us a form for the integral, the square root a squared plus u squared du. And the table reads that this integral is u over 2 times the square root of a squared plus u squared plus a squared over 2 times the natural log of u plus the square root of a squared plus u squared, and then plus some constant of integration. So we're not actually going to need this constant of integration. So with that, our arc length, which was again the integral from 0 to 2 pi of the square root of t squared plus 5 dt. Well, in this form, our a squared is 5, and our u squared is t squared. So we'll have t over 2 times the square root of, and since addition is commutative, I'm just going to write it as t squared plus 5. Plus, now this 5 halves times the natural log of t plus the square root of t squared plus 5. And this whole thing is evaluated from when t equals 0 to 2 pi. So plugging 2 pi in first, we'll get this is equal to pi times the square root of 4 pi squared plus 5 plus 5 halves times the natural log of 2 pi plus the square root of 4 pi squared plus 5. Now we have to subtract at 0, so it'll become minus 0 minus 5 halves times the log of 0 plus the square root of 5. So our final answer will have pi times the square root of 4 pi squared plus 5 plus 5 halves times the natural log of 2 pi plus the square root of 4 pi squared plus 5 minus 5 halves times the natural log of the square root of 5. And now we can use laws of logarithms to combine these last two terms to write out pi times the square root of 4 pi squared plus 5 plus 5 halves times the log of 2 pi plus the square root of 4 pi squared plus 5 all over the square root of 5. And this here is our arc length. All right, so now we're going to look at what's known as the ArcLength function. So if a vector value function represents the position of a particle in space as a function of time, an ArcLength function measures how far that particle travels as a function of time. The formula follows directly from the ArcLength formula. So the ArcLength formula, remember, was S is equal to the integral a to b of the magnitude r prime of t dt. So to turn it into a function, we just say s of t is equal to the integral from a to t of the magnitude of r prime of u du, where a is the starting time. Now, since s of t measures distance as a function of time, s prime of t would be the speed of the particle as a function of time. So s prime of t is d dt of that integral. And by the fundamental theorem of calculus, these two will drop out and we'll be left with the magnitude of r prime of t. If we assume that r of t defines a smooth curve, then this magnitude will be greater than 0, which means the speed will be greater than 0. And finally, if r of t is a curve on which the magnitude of r prime is 1 for every value of t, then s of t would simply just be t minus a. And this means that t represents the arc length as long as a is equal to 0. And all of that is summarized in this theorem. Now, what do we use the arc length function for? Well, one of the most useful applications is to find an alternative parameterization of a curve, and we call that the arc length parameterization. So let's suppose that we find the arc length function s of t and are able to solve this function for t as a function of s. We can then reparameterize the original function r of t by substituting that expression t of s back into r of t. That will then give us a function r of s. So we'll look at that now in this example. So we're going to find the arc length parameterization for the curve given by 4 cosine t, 4 sine of t, where t is greater than or equal to 0. So the first thing we need to do is we need to find the arc length function. So to do that, we first need r prime. So negative 4 sine of t, 4 cosine. Then we can calculate its magnitude. Square root 16 sine squared plus 16 cosine squared, which is just the square root of 16, which of course is 4. So the arc length function is the integral from the starting time 0 to t for du. So it's just for u when t is 0, I'm sorry, when u is 0 to t, and it's just for t. Solving this for t will give us t is a function of s, and it's 4 over, I'm sorry, s over 4. So this is known as our arc length, or this s is our arc length parameter. So our arc length parameterization, r of s, would be 4 cosine of s over 4 and 4 sine of s over 4. Right, and since t has to be greater than or equal to 0, we can say that s must also be greater than or equal to 0. So let's look at another one. This one is a space curve. We'll look at the space curve defined by the vector t plus 3, 2t minus 4, and 2t, where t has to be greater than or equal to 3. Okay, so our prime of t would be 1, 2, 2. So this magnitude would be the square root of 1 plus 4 plus 4, which is the square root of 9, which is just 3. So arc length function is the integral from the starting time 3 to t of 3 du. So we get 3u evaluated from u equals 3 to t. And so we get 3t minus 9, or 3 times the quantity of t minus 3. Solving this for t is a function of s, we get t of s is equal to s over 3 plus 3. So our arc length parameterization would be s over 3 plus 6, because remember all we're doing is taking this s over 3 plus 3 and plugging it in everywhere we see a t. Then we'll have 2s over 3 plus 2 and 2s over 3 plus 6. Now, since t has to be greater than or equal to 3, this means that s would have to be greater than or equal to 0. Now, we can use this arc length parameterization to find a new measure for a curve, and we call it the curvature. And curvature provides us a way to measure how sharply a smooth curve turns. That is, how curvy a curve is. And we define curvature, let C be a smooth curve given by R of S. So notice that we're not using R of T. We're using the arc length parameterization R of S. Then the curvature, kappa, this is the Greek letter kappa. So let me just write that down. This is kappa at S is simply kappa of s equals the magnitude of the derivative of t of s. Well, this provides a bit of a problem. This is not exactly practical or useful for calculation purposes, right? It first requires us to find the arc length parameterization. Now, the two examples we did were simple because the magnitudes were constant. Most curves will not have a constant magnitude of r prime. So that is a bit of a pain. Then we have to find the unit tangent vector of this parameterization. And that can be quite a pain. Then we have to take its derivative and find its magnitude. So this whole process is rather tedious. However, by the chain rule, we can write dt, so the derivative of the unit tangent with respect to t is the derivative of the unit tangent with respect to s times ds dt. If we divide both sides by ds dt and then take the magnitude, we'll wind up with the magnitude of dt ds is equal to t prime of t over s prime of t. And using properties of magnitudes, it's the absolute value of 1 over s prime. However, recall that we showed that s prime is always positive. So it's 1 over s prime times the magnitude of t prime. And s prime is simply the magnitude of r prime. And so we get that the magnitude of dt ds is equal to the magnitude of t prime of t divided by the magnitude of r prime of t. But this piece here was the curvature kappa. And so we get kappa of t is the magnitude of t prime of t over the magnitude of r prime of t. However, this can still be quite tedious, because calculating the unit tangent vector can be quite tedious. But recall that the unit tangent vector is defined as r prime over the magnitude of r prime. So what we're going to have is r prime of t is equal to ds dt times t of t. So if we take the derivative now, we find that r double prime is a product rule. So the t prime, the second derivative of s with respect to t times t plus ds dt times t prime. If we now look at the cross product, r prime and r double prime, right, it'll be ds dt times t crossed with d squared s dt squared times t plus ds dt times t prime. We can use properties of cross products to say, well, this is going to distribute in, so it'll be this term cross this term plus this term cross this term. We're going to wind up with a t cross t. Any vector cross itself is always the zero vector. So this first term is just 0. So all we're left with is this here, s prime squared times t cross t prime. Now, t dotted with t is the norm of t squared. That's a property of dot products. But t is a unit vector, which means this magnitude is 1. So we have 1 squared is 1. This means that t dotted with t prime is just 0, which means that t and t prime are orthogonal to each other. That is, the angle between them is pi over 2. So if we now take the norm of this, it's the norm of this. Well, this is just a real valued function, so we can take it out as an absolute value. But again, this is always positive, and it doesn't matter because the square is always positive anyway. So we don't need the absolute value bars here. And we're left with the norm of t cross t prime. Well, the norm of a cross product is the product of the norm of the vectors times sine of pi over 2, or times sine of the angle between them, which in this case is pi over 2. Now this is unit, so that magnitude is just 1. Sine of pi over 2 is 1, so we're left with s prime squared plus the norm of t prime. This is the norm of r prime, so it's the norm of r prime squared times the norm of t prime. If we solve for the norm of t prime, it is the norm of r prime cross r double prime all over the norm of t prime squared. If we divide both by the norm of r prime, then this left-hand side will become kappa, and we have kappa of t is equal to the norm of r prime cross r double prime all over the norm of r prime cubed. Now what if we're given a curve that is not defined parametrically? That is, it is in the form of y equals f of x. Well, in that case, we can write it parametrically as x, f of x, 0. So r prime would be 1, f prime, 0. And r double prime would be 0, f double prime, 0. So now if we take the cross product of r prime and r double prime, we will get the vector 0, 0, f double prime. Now we plug it into the previous formula. And that'll give us that kappa, now as a function of x, is the absolute value of f double prime over the square root of 1 plus f prime squared cubed. Replacing f of x with y, and we can write kappa of x is the absolute value, of y double prime over the square root of 1 plus y prime squared all cubed. So those three boxed equations can be used interchangeably depending on the situation. So it depends on the situation, you can use any of them. Typically, I will use the magnitude of r prime cross r double prime over the magnitude of r prime cubed if I'm giving a vector parameterization. And if I'm given a curve that is defined as y equals f of x, I will use this one. So let's look at the curvature of a circle. So circle of radius r. This circle has the parameterization of r cosine t, r sine of t, for 0 less than or equal to t, less than or equal to 2 pi. Well, to take a cross product, it needs to be a vector in space. So what we can do is represent r of t as a vector in space by setting the last component as 0. So now if we take the cross product, r prime cross r double prime, we get the vector 0, 0, r squared. So the magnitude of this would be r squared. And the magnitude of just r prime is r. So you plug it into that formula. Kappa is r squared over r cubed, which is just 1 over r. That is, the curvature of a circle is inversely proportional to its radius. What this means is that the larger the radius is, the smaller the curvature. That is, the shallower the curve. Right, so if we look, here's a circle of small radius, right? It's got very steep curves. If I now try and draw a larger circle, right, the curves aren't as steep. So it's a little less curvy. And in theory, if you let the radius grow to infinity, it has no curvature. Its curvature would be 0. And again, in theory, if you let the radius go to 0, then the curvature would become infinite. We now define two new vectors. So we're going to let C be a three-dimensional curve represented by R over an open interval I. If T prime is not 0, that is, if the derivative of the unit tangent is not 0, we define the principal unit normal vector at T as T prime over the norm of T prime. So the principal unit normal vector is a vector that is tangent to the unit tangent vector, which by definition would make N and T normal or orthogonal. That's why it's called the unit normal vector. Then we define the binormal vector as the vector that is orthogonal to both the unit normal and the unit tangent. And so it would be T cross N. So we are going to find the unit normal and the binormal of this curve. Right, so remember the first thing we have to do is find the unit tangent. So we need R prime first. So that is 6, 10t, and negative 8. So this would mean that the magnitude of R prime is the square root of 36 plus 100t squared plus 64, which is the square root of 100t squared plus 100, which is just 10 times the square root of t squared plus 1. So our unit tangent is 6, 10t minus 8 all over 10 times the square root of t squared plus 1. We can factor a 2 out of the numerator, and so we'd be left with the vector 3, 5t minus 4 all over 10 times the square root of t squared plus 1. We now have to take the derivative of this. So using properties, it'll be the derivative of the vector times the scalar function. So we're going to have 0, oops, I'm looking at the wrong one, 0, 5, 0 over, and I'm sorry, this down here should not have been a 10, that should have been a 5, over 5 times the square root of t squared plus 1. Then it is plus the vector 3, 5t minus 4 times the derivative of that scalar function. So still be over 5 times, 1 half, negative 1 half t squared plus 1 to the minus 3 halves, then times 2t, Draw an arrow to show that that gets multiplied there. So this is now equal to 0, 1, 0 all over the square root of t squared plus 1 minus t times the vector 3, 5t minus 4 all over 5 times t squared plus 1 to the 3/2 power. And if we add these together, we get negative 3t, 5, 4t all over 5 times t squared plus 1 to the 3/2 power. So what we now need to do is we need to take the magnitude of this vector. Let's do that on the next slide. So the magnitude of t prime of t, right? Well, it's the absolute value of the scalar, so it's going to be the absolute value of this down here. Well, this will still be positive, so 1 over 5 times t squared plus 1 to the 3/2, then times the magnitude of the vector, so square root of 9t squared plus 25 plus 16t squared, which is the square root of 25t squared plus 25, which is 5 times the square root of t squared plus 1, and I kept forgetting these, so this will be over 5 times t squared plus 1 to the 3/2. This is over 5 times t squared plus 1 to the 3/2. Redraw this line so it's not equals. The 5s will drop out. We're left with 1 over t squared plus 1, right? Because then this and that will drop out. Therefore, our normal vector, our unit normal, is 1 over this, so t squared plus 1, times t prime, which was negative 3t, 5, 4t, all over 5 times t squared plus 1 to the 3/2. This will then equal the vector negative 3t, 5, 4t, all over 5 times the square root of t squared plus 1. So here is our unit normal. If I go back, this here was our unit tangent. And we're going to need those two because we now need to find the binormal vector, which, remember, is t crossed with n. So pull out this 1 over 5 square root, pull out this 1 over 5 square root, multiply them together. We wind up with 1 over 25 times t squared plus 1. Then we're going to have a determinant. So the t vector, 3, 5t minus 4, 3, 5t minus 4. Then the normal vector, minus 3t, 5 and 4t. So we still have this 1 over 25. 25 times t squared plus 1. And we're going to have a vector in the numerator. So the I component will be 20t squared plus 20. The j component would be negative 12t minus 12t. And the k component is 15 minus 15t squared. Well, this middle piece here, this j component, winds up just being 0. And there is a 5 common in the I and k, so this becomes 4t squared plus 4, 0, 3 minus 3t squared, all over 5 times t squared plus 1. Now, if we look, we factor out a 4 from the first, factor out a minus 3 from the last. Each term will then be left with a t squared plus 1, which will drop out with that denominator. And so we get the vector 4, 0, negative 3 over 5 as our binomial vector. And that concludes our study of the arc length and curvature, as well as the two new vectors, the unit normal and the binormal.